Hi all, my name's Tovio, and this is another Galvanize DSI Prep Study Hall. So feel free to post questions in the Slack, wherever you're stuck, and I will get to them in the order that they're received. And otherwise, I'll just do some exploratory coding. We're heading into we're a couple weeks out from the deadline for the technical interview for our October DSI. So I'm going to be probably doing a lot of things with dictionaries. So I'll code some functions and I'll try to kind of spin anything that we look at toward dictionaries in some way. I think that can be helpful, especially if you're feeling shaky on dictionaries. But feel free to ask questions on anything. If you feel like what's happening is going over your head, and you're stuck somewhere, somewhere in intro Python on a challenge that feels like maybe it's too easy and maybe you shouldn't ask about it. Just ask about it. Just post a link to the challenge and question in regards to it, and I will go over that challenge. I'll just code it through and talk it through, and we can sort of focus on those things. So this is not like a linear kind of thing, right? I do kind of work steadily forward through the learned materials, but for the most part, I kind of asynchronously address questions as they come up, and I'll try to make things look more and more like the technical interview for the sake of those of you who are studying for it. So I have up here just, variance of a population, variance of a sample. We kind of left off here a couple sessions ago. So I'm just going to code these out. I'm going to code out variance functions. And, excuse me, these are pretty straightforward. Okay, so, pardon me. Let's kind of pick this apart first. So variance gives you a sense of the spread of some data. We often call this we describe this in terms of the spread of the data. How far data is spread around the mean. And we can kind of see this. If you're familiar with Euclidean distance, kind of this part looks like it looks like a distance measurement. We take the difference of two items and we square it. That gets rid of the negatives. We sum it all up, and here we're dividing by the number of items in the list, and that gives us the variance. Variance is often represented as sigma squared or s squared, depending on whether or not we're dealing with a population or a sample. Notice there is a difference here between the population version and the sample version, and that's just, there's a couple small differences, but the primary difference is here. We've got Bessel's correction here, and this lessens the bias of our variance, and that's why we apply it. So here we've got the mean represented as mu, Greek letter mu, and here we've got the sample mean represented as x bar. But at the end of the day, these are very similar, and the difference here that you want to consider is if you have all the data from a population, then you can go ahead and use this version. And in almost no case will you have all the data. So in general, you're going to use the sample version, and we can think about this, right, as a sample from a population, right? So in some sense, we're trying to effectively estimate the mean and the variance in general when we're sampling from a population, because we very rarely have the resources to have all that data in front of us, the entire population data. So let's just write this. I'm going to write a variance function. I'm just going to call it variance. Maybe I'll make this a little bit bigger. Def variance, and I'm going to pass in a list of numbers. And we're going to assume that this is a sample, but we want to make space for it potentially to not be a sample. And I'm going to do this with a simple kind of accumulator pattern. So I'm going to set a total, and I'm also going to get the mean. So what this means, you know, as we saw, we need the mean of the data. And in either case, whether it's mu or x bar, whether it's population or sample, we're going to need that. So that necessitates writing another function. So I'm just going to, you know, this is a little bit overkill, but, you know, I'll just say this. To do, I'm going to complete the function, and I'm going to write another function called mean. Mean is going to take in a list. And, well, how do we calculate the mean? That's pretty simple. We just sum all the values and divide by the length of the list, right? So we can just return the sum of the list divided by the length of the list. Okay, so now we've got a mean function, and we can just continue back to our variance function. So a way that we can do this, a way that we can calculate this variance, we can just say for each item in the list, well, let's increase the total. The total is going to get the item minus the mean, right? That's what we're seeing over here. I should just leave this up. So the item, right, minus the mean, or, you know, same thing down here, item minus the sample mean, and we square that. Oh, it looks like somebody, 1 second, somebody's asking about the location of the stream, so let me just connect them to that. Okay. All right, so we're building this total, and notice I'm kind of doing this first, right? I'm doing this part first. And this part is essentially, this is the same mathematical operation, right? There's nothing different here. The only difference is the symbols that we're using. We're using mu or x bar, as opposed, you know, we're using mu in the population version and x bar in the sample version. So the only real difference is over here, where we either do or we don't, like we don't apply Bessel's correction or we do, right? And so if that's the case, we can just use this switch up here, this sample, and we can use that to finish off the logic in our function. So at this point we've got the total, and I can say if it's a sample, then I can return the total divided by the length of the list minus 1. Be careful not to make this mistake. I make this mistake more often than I'd like to admit. Order of operations, right? Subtraction comes after division, so we just need to wrap this in parens. And if it's a sample, do that. Otherwise, return the total divided by the length of the list. And so how do we test this? Oh, whoops. I actually have a logical error in here. Mean is a function, and I'm saying item minus this function named mean. This actually needs to be mean underscore. So let me fix that. All right. So the first thing I'm going to do is I'm going to generate some random data. And to do that, that should be pretty easy. Let's say I'm going to generate some random data. I'll do this in a comment. Generate random data, let's say numbers between, I don't know, 0 and 200. Do it like that. And I'll just call this a number list. And I'll generate 20 random numbers. So why don't I write another function just to drive this idea home. Let's call this. Huh. Interesting. It looks like people are having a hard time connecting to the stream. Let me just verify that the stream is happening in a way that makes sense. Okay, I'm actually trying to troubleshoot this now. I may have provided an incorrect link. To the stream. Oh, great. Looks like YouTube has changed. Okay, I'm sorry. If you're just jumping on the stream now, it looks like YouTube has changed their convention overnight, maybe. And it looks like now they're giving a randomly generated URL for the stream, which is pretty inconvenient from my point of view, given that we have this live link shared in a bunch of places. You know, so that kind of means I have to go change a bunch of copy in a bunch of different places. Cool. Yeah, I don't know. They're completely changing the way they do streaming. Like, there's a different streaming dashboard, and I've tried multiple times. I've yet to be able to get it to work. And when I have gotten it to work, sorry, I haven't gotten it to work as I expect it should. And when I have gotten it to work, I haven't been able to find the URL to share where people can watch the stream. So I'm a little, Anyway, I'm sure I'll figure it out. It's probably not that complicated. I just, you know, sometimes struggle with basic technology, as probably not that many of us do. Cell phones are a mystery to me. That's not true. Okay. So I was going to write a function to get samples. So I'll just call it get samples. And if you're just joining, I wrote a variance function based on these two different equations, either population or sample, and that calls out to a mean function. And now I'm writing a function to get samples on which we can get the variance. So what might I want this to do? Well, maybe I want to specify the number of samples, right? And maybe I'll set a default to 20. So, you know, you might imagine that's a fairly small set of numbers to consider. And let's also think of these samples as being whole numbers, just for our purposes here. We could get, you know, numbers with decimal values. We could work that out. But I think it's fine to demo variance from a perspective of whole numbers. And so I've got 20 samples by default, and maybe I want to have a low value. So a low, you know, the low end of my sampling range, and maybe I'll do 0, and then the high I'll do as 200. Okay. So easy way to do this would be, you know, I make an empty list, and then I say for whatever, however many, in range. That's what this underscore is. This is just, since I'm not going to use it, I could say for I in range, but since I'm not going to use it, I'm going to say for underscore in range. I'm going to go from low to high, and I want to be inclusive of high here, so I'm going to do high plus 1. Oh, sorry, I'm being dumb. For whatever in range 20, because I want 20 samples, then I'm going to say out.append, and this is going to be my samples list. Okay. I'm going to make a choice from the samples list. Now this choice function, I'm going to go ahead and just import this. So I'm going to say from random import choice. And what choice is going to do for me is I can pass in some sequence, some list here. I'm going to make a samples list. And it's going to give me a random value back from that. So if I were to run choice on, 1, 2, 5, it's going to give me a 1 or a 2 or a 5. It's going to give me an item out of that list. So out.append choice samples list. Now I still need my samples list, right? I haven't made this. The way I'm going to make this is pretty simple. I'm just going to say sample list gets, it's going to get the range from low to high plus 1. And I can cast that as a list. I don't necessarily need to. Choice will actually pull this out without me casting it to a list, but if I want to look at it, then, if I want to look at this samples list and not just look at the generator object, I'm going to cast it to a list. That said, no good reason actually to cast it to a list. I'll just do that. Okay, so now I can return out, and this should get me 20 random values. Excuse me. So I'll just copy this, and why don't we say numList gets these samples, and let's print the numList. And I'll just say Python dummy.py, and that gives us 20 numbers in the range from 0 to 200. So that's nice. We can do that. Now, if I run this again, we're going to get 20 different numbers. So that might make it hard to do. It might make it hard to do certain analytic approaches with our function. So I'm actually going to set a random seed. So I can do this. I'm doing from random import choice. I'm also going to import seed. And the way that I'll do this, within my get samples function, I'm just going to set the random seed. So seed I'll set to 23. And let's see if that makes this number list consistent, this randomly generated number list consistent. So it starts with 199, 74, 21, 4. And notice having set a random seed gives me reproducibility in these lists. Okay. So now that I have this list, we can look at the variance on the number list. So I'll say print, and let's look at the variance on the number list. Remember, we're assuming that it's a sample, but I'm still going to just go ahead and put sample as true in here. And let's see what we get. Okay, so our variance is 3,497. How do we interpret that, right? That's a fairly strange number to try to interpret, given that our range of values is between 0 and 200. How do we have a variance of 3,497? Well, it turns out there's the variance is sort of out of scale, right? This is a squared value. We can see that here, right? When we say, when we build this total, we're saying item minus the mean squared. And we can see that over here, right? We can see that pretty directly. We're taking this out of scale. And if we want to bring this back into scale, we can use another measurement called the standard deviation. And yeah, pretty easy to do that. We just take the square root. And so there's something kind of intuitive about this. We sort of use squaring to take us to get rid of the negatives when we're doing a summation, and then we take the square root in order to we take the square root in order to bring it back into scale. So in this list of numbers, we're trying to interpret a variance and we might have a tricky time doing that. We might have an easier time interpreting the standard deviation, okay? So again, I'm going to make the standard deviation. I'll do this similar to the variance. I'll say standard deviation of a list, and then we'll assume that it's a sample, although we can use this on a population as well. And we'll go ahead and utilize this variance function that we already wrote. So if I call it to variance, I can just say the variance gets the variance on the list that we passed in, and instead of sample gets true, I could just say sample gets sample, or I could just say sample, right? That will work as we would want it to. And then I can just return the variance, the square root of the variance, which I could import from math the sqrt function, which is square root, or I can just raise it to the power of 1/2. And I tend to do this. So this is on more lines than are necessary. I can condense this down to 1 line. And I can just return all of this. So let's return that variance. And let's, instead of calling to variance, let's call to standard deviation. Okay. So we have a standard deviation of 59. And if you think about our mean, well, why don't we print our mean on the number list first? So let's print the mean of the number list. Oh, it's actually called, there's an I in it, that's why. Okay. So 87.25 is our sample mean, and we're expecting most values to fall somewhere in the, the average distance between each data point and the mean is 59. Okay, well that kind of makes sense, right? If we look at this list and we think about, what was it, 87.25, you can imagine that the average distance between each data point and 87.25 is going to be this 59, roughly 60. That makes sense. If we change the random seed, of course, we're going to get something different. Maybe I'll change this to 42, and let's see what we get. And I'll also print out the number list while I'm at it, so we can just take a look at it. Okay. Okay, so now our mean is around 84.95. Okay. And our standard deviation is around 69. So, we could, we want to keep in mind that we're dealing with a sample here. And we could take for granted this estimated standard deviation. We could also we could take another approach where we build a dictionary and we what would be a way to do this? What would be a good way to do this? So I'm going to get rid of this seed. Let's not even consider having a random seed. And so every time that we run this, we're going to get different values, and those won't be predictable. Okay? So let me just run this a couple times. Okay? Now we have a mean of 110. We have a mean of 118. We have a mean of 119. We have a mean of 81. A mean of 101. Okay. So the first thing that I'm going to think about in terms of the mean is I guess I'm going to call out to this function a certain number of times to our get samples function. I'm going to call out to it, let's say 1,000 times or 10,000 times, and I'm going to build a dictionary where we, I guess we could bin the mean values. Okay, so we can look at a distribution of the means. Why don't we do that? So I'm going to call this distribution of the means, and let's use the same parameters or similar parameters to this get samples. So yeah, let's just grab this. Remember, num samples is how long our list is, our list of samples. Low is the lowest value that's possible, high is the highest value. We want to do this a certain number of trials. And if you've watched my videos before, don't be confused. I'm using num samples here and num trials here. Usually I would actually call this num samples, but I'm going to call it num trials. A trial here is a single trial is a single instance where we call out to our function, our get samples function, right? So a single call to this is a single trial. We're going to do this a certain number of times, and by default I'm going to do 10,000. And I'm going to kind of get rid of these so that we use the parameters, the arguments that are passed in. Okay, so if we're going to do this num trials times, well, if we're going to do this num trials times, and we're going to pack in our means into some kind of histogram, I'm probably going to use a dictionary. So let me do that. I'm going to make a dictionary, and I'm going to say for whatever in range num trials, that's how many times we're going to do this, I'm going to get a sample list, right? I'm going to call this sample list, and it's going to get some samples, right? Number of samples, which is up here, currently at 20. We'll leave it at 20. Low of 0, high of 200. And I'm going to get the mean of that. So I'll call this, I'll just call it x bar for our sample mean, and I'll get the mean of the sample list. Okay. So x bar is going to have a decimal value, and maybe the keys in my dictionary are going to be bucketed by whole numbers. All right. So just to keep it simple. And maybe the way I can do this, I'll say if, well, maybe I'll do it like this. So I'm going to make a key string, and this is going to be an F string, and I'll say this is greater than or equal to the int of x bar. So maybe I'll also do this. So I'm going to just add another line. Don't really need to do this. The x bar, I'll call it the x bar bucket, is just going to get the integer of the x bar, right? So I'm just dropping off the decimal value. I could use the floor method, but this is fine for me. So I'll say it's going to be greater than or equal to the bucket value. So why don't I do this? The bucket value is going to be less than or equal to x, which is less than the bucket value plus 1. And I'm just doing this to make some nice keys, some pretty dictionary keys. This is something that you might not need to do something quite this complex, but you'll need to be able to do something like this for the technical interview. So I'm going to say we've got our dictionary, and I'm going to say d sub x bar, well, d sub key string is going to get something. It's going to get incremented by something. Now, the thing is, d sub key string may or may not exist. So I need to check to see if it exists first. I'm going to say if key string not in d. So if it's not in there, then we're going to add it in. And right now I'm going to make a choice, right? I'm going to say, I'm going to make a choice. Do I want counts of this, or do I want lists that I then append to? And if you imagine what that means here is that the list is going to be, if I do a list, then I'm going to put into this list the different means that are generated, these different x bars that are generated, okay? So if key string not in d, d sub key string gets initialized to an empty list, and then in every case, why don't we do it like this? In every case, we're going to append x bar, okay? So at this point, I can just return d. And I'm going to say for k, v in, let me get d out of this. Our distribution of means, we'll use all these default values. Yep, because this falls in line with what we've already done. So for k, v in d.items, I'm going to print, I'll do this. I'm not going to print all the means, but I'm going to print some of them. So I'll print k, and then I'll do v, and I'll just do the first 5, let's say. And maybe I'll even do something else where I do a count, where my count is just the length of those lists. So I probably have some errors in here. Let's find out. Amazingly, I do not. Okay. So this might be tricky to interpret, in part because it's all out of order. Remember that dictionaries don't guarantee order, so I'm just going to go ahead and sort this whole thing, and I think that'll help it be a little more orderly. Okay. All right. So the lowest mean out of 10,000 samples that I got was 100. Is that correct? No, it wasn't. Okay. I see what's happening here. The lowest mean that I got out of all those samples was 56. 56.2, it looks like. And so, this is a little bit out of order, but that's okay. So we go from 56 up into 99, and then notice, because these are strings, they're not sorted in the order we'd expect numerically, because 1 comes before 5, right, in strings. So we go all the way up to a mean of 143, 143.85, 143.05. Something to notice here is that these counts, as we approach where I think the mean is, the theoretical mean, given how we generate our numbers, as we approach the theoretical mean, our values go up. So I think our theoretical mean is somewhere around 99, 100, right? Because we're going from 0 to 200. And notice the count for that is 309. Okay. The count for 100 is 304. So and 101 is 315, sure. But if we were to run this a number of times, I think what we would see is similar numbers, and we would center around some theoretical mean. So we would be approaching a theoretical mean. So how might we do that? There are a couple ways we could do that. You know, what I'm going to do is just write another function, and maybe what I'll do, let me think about a good way to do this. I'm going to write a function that just gives us counts instead. So I'm going to take this almost. I'm going to take some of this. I'm going to take at least that much of it, and let's go ahead and say, let's modify this just a little bit. Distribution of means counts, and 20 samples, low, high, 200. You know, we can leave all that. So for I in range, for whatever in range, the number of trials, we're going to call out again to this sample list. And we're again going to grab the mean, the X bar from that, and the X bar bucket. And in this case, I'm just going to use the X bar bucket as our key, just so that we can look at this in order, and it'll be a little more convenient. So if X bar bucket is not in the dictionary, then we'll say D sub X bar bucket is going to be, it's going to start at 0, because we're doing counts now instead of lists. And then I'm just going to increment this by 1. And I can just return the dictionary. Okay. So let me borrow this code from up here. This is going to change only slightly. So this is a distribution of means counts. And we can leave all that the same. For KV in the sorted version of d.items, print, let's just print the K, and we can print the V, right? Because that is just a single value now. Okay. So let's take a look at this distribution. Notice our highest numbers are occurring right around 100, right? And you might wonder, well, how do we start approaching the theoretical mean with this concept? The way that I'm going to do that is I'm going to take this, kind of take this whole function, and I'm going to write another function called estimate theoretic mean. And I'm going to build a dictionary again. Same kind of thing for whatever in the range number of trials. I'm going to do something, but this time it's going to be a bit different. Instead of calling out to get samples, I'm going to actually get a dictionary out of this. I'm going to get the distribution of means counts. So that's going to be D, I'll call it means counts. And it's going to get the distribution of means counts. Number of samples, we're just going to use the value that's up here. Low, high, and num trials. And we'll leave that at 10,000. If you imagine at this point, we're doing 10,000 times 10,000 times 20. There's a lot of loopage happening here. But I might need to lower this. I'll just lower it now. Yeah, I'll lower it now. That's going to help us. So D means counts. Remember, this is going to have keys that are the mean buckets and counts of the occurrences of values that fall in those buckets. So if I'm calling out to this over and over again, then I can just say, I can do something in here for kv in D means counts dot items. If k not in D, then D sub k is going to get initialized as a list, and then D sub k is going to have appended to it the value. Okay, so that is going to get us a dictionary. At this point, it's going to get us a dictionary that has keys as the buckets and values as the counts of means that fall in those buckets. I'm going to take this one step further, though, and we're going to settle on, we're trying to find the bucket that is modal, right? So this is the modal bucket, and we're doing that by sampling out for all these means. If we wanted to, well, I'll do this other thing next. Before I won't get ahead of myself. We're finding the modal bucket. What is the bucket that we can expect our means to fall into, right? So I'm going to say for k, v, and d this time, d dot items, d sub k is just going to get the sum of v, right, divided by the length of v. Oh wait, we already have a function that does this. It's going to get the mean of v, right? So now we can just print this out, and what did I call this? Estimate theoretic mean. How about we call it estimate theoretic mean bucket. I don't know. I'm just trying to not be too inaccurate if I can help it. All right, estimate theoretic mean bucket this time. And again, we're using all of our same default parameters that we were using before. So let's go ahead and find out about this. Let's find out that it has invalid syntax on line 92. I'm just missing a colon. I can tell that by this. It says syntax error. I know I should have a colon there. It was easy enough to find. There's some other error. Estimate theoretic mean buckets. Huh. Well, I don't know what the error is actually. Float object has no attribute append. Okay. If k not in D, D sub k gets... Interesting. On line 95. Why is D sub k a float? I believe I'm making D sub k happen right here as a list. Let's just figure this out. Float object has no attribute append. I'm gonna print D sub k and see what it is. 31.0. Okay. Yeah, I'm trying to figure this out. I'm not sure exactly what I'm doing wrong here. D sub k dot append v. This is where my error is. 31 is printed as d sub k, so d sub k is 31 at some point. Where am I modifying d? Oh, what is happening there? So here's d. Oh. It might just be that. Okay. Float object still has no attribute append. All right. On line 96, same thing. Yeah, if you see my error here, if you're watching and you see my error, let me know. I'm a little bit at a loss as to what's happening here. Okay, so mean buckets, num samples 20. Okay, for whatever in range, num trials, d means counts. Let's just print. Let's print d sub k at this point again, because, oh, I see. I think I see what's happening here. Yeah, notice that after it builds D once, right? So we've got D, and we initialize all of these values to lists, and that's exactly why. Oh my gosh. This was nested under this for loop, and it should not be. This should definitely not be under that outer for loop. Because after I do all this appending, that's when I want here. I'll just run this and we'll have a clearer idea. Okay, so notice this is giving us a ton of lists. I'll just kill it really quick. This is giving us a ton of lists, and these lists are growing and growing in D. Of course, we don't really want to print that or anything, but at the end of the day, we want D sub k to get the mean, right? So we're overriding all those lists with just the mean from those lists. All right, this should be meaningful. Okay, so we're doing this 1,000 by 10,000 times. So that didn't take too long. Wasn't the shortest thing in the world, but these are our estimated counts, and we should be able to find our modal bucket, and I think this should make sense, right? It's 99 and 100. These are very close to each other. So we would expect a value between 0 and 200. We would estimate the expectation to be, between, say 99.5. Okay, so this is an approach for just analyzing the outputs here. Like, it's just exploratory, and I don't think we're too surprised about what we're seeing. Now, you're going to want to take exploratory approaches to problems pretty often. Okay, and this is just an example. It's nothing. It's nothing that's on the technical interview per se, but everything skill-wise that I just did in here is on the technical interview in some form. Okay, so distribution of means counts. Now, what if we just want to generate a bunch of samples and try to figure out what the mean of the means is more directly? So I'm going to just write something called, I'll write something called mean of means. And let's do num trials of, yeah, we still need all of this. Let's do mean of means. Let's do num trials of 1,000. And in this case, I'm going to just say, I'll just make a means list. And we'll make that just an empty list. And I'll call out to this get samples again. And what I can do here is just, this is just our samples list. I can, you know what? I'm going to do this in an even more straightforward way. I'm going to say this is a samples list, right, which is a list of lists, or will be. And I'm going to say for whatever in num trials, and I'm going to say samples list dot append this get samples. Okay. And we can take a look at what samples list is. It's going to be 1,000 lists of 20. And I can get the mean for each one of those lists. So I'm going to say this is the mean list. And I'm just going to do this in a similar collector pattern. So our means list is going to have, we're going to say for, let's say sample list in samples. Let me make these names make a little more sense. Sample lists, and let me rename this as well as that. Okay, so sample lists dot append, and then now we say for sample list in sample lists, means list dot append the mean of the sample list. Okay, and so now we have a means list that is full of the means, right, from all these samples, from 1,000 samples. And now we can just get the mean of the means list. So let's just return the mean from the means list. This is the mean of means, right? And I'm going to go ahead and print mean of means, and we'll leave all those default values in there and see what we get. We get an error. Okay, so on line 112 in mean of means for whatever in number of trials. Huh. Int object is not iterable. Oh, well, of course it's not. For whatever in range number of trials. That's all that is. I just forgot the range function. Okay. So look at that. 100.452. So, oh, I think I said something like it's between 99 and 100 before. What I meant to say, if I was thinking about it rationally, would be it's between 100 and 101. And that's because, we're going between 0 and 200 inclusive, right? So the value that we would have as an expectation in that range is 100.5. So let's run that again. And now, Or is it 100.5? You know, it might just be 100. I'm looking at this, and you know, this is just my, it's just 100. But look, we're floating between 99 and 101. We're not quite hitting 101. We haven't yet, but I'm sure if we did this over and over again, we would settle somewhere. So should we do that? Should we do the mean of the mean of the means? We could. So, you know, that's as easy as saying, I'm just gonna write it just for fun, mean of means, and we'll just pass in all the same stuff. And this is gonna take a little bit longer to run, right? Because we're dealing with number of trials. In this case, we can just call out to mean of means, and I'm going to say, I'm just gonna return the mean of, let's say for m in range, actually let me do it like this, mean of means, because this is returning a single scalar value, right? This is just giving us a float return, and I'm gonna do this a certain number of times. I'm gonna do this for whatever in range num trials, and let's see if this takes too long. Oh, great. There we go. I didn't actually call anything, so let me call this function, and let's print the result. And I would assume this is going to take a little bit, right? Because we're running each of these 1,000 times. There we go. So notice this is settling right around 100. And yeah, I think that is our expectation, given our scheme for generating numbers. And I think if I increase the number of trials on this, what we would end up seeing is this would be more precisely heading toward 100. So if I run this again, you know, we might actually get a little bit below 100, but approaching 100. And you know, I could do the, and we did, right? So 99.989. If I ran this over and over again, I could even write another function called the mean of the mean of the mean of the means. I'm not going to do that, but you know, this is just me sort of proving a point that as we sample, and we continually sample from our samples, we're approaching an expected value. Now, this is nice. This is all in good for the mean. It turns out it's not quite that simple for the variance and standard deviation. And for a couple reasons, and I'll just talk about the variance. So there's an assumption that we're making when we perform Bessel's correction here. When we perform Bessel's correction, there's an assumption we're making that we're trying to better approximate the population standard deviation, right? And this is helpful. Don't get me wrong. Bessel's correction is helpful, but notice that in this case we know the mean, right? We know the mean, and in this case we don't. In this case we don't. Now, this is an issue with Bessel's correction if you're trying to approximate the population variance, because this mean is going to have its own. It's going to have its own variance, right? We can see that. We've already seen that in this code, in the output for the mean of means, right? In this sample list of means, in this means list, there's going to be range. There's going to be a range of values. And we really saw that in the theoretic mean bucket, right? So it just kind of creates a little bit of an issue in deciding that we are approximating the theoretical or the population mean. Like we're like, hey, we're approximating the standard deviation or the variance. We're approximating the variance of the population if we do this. And actually, we're removing bias when we do this. We're not actually approximating the variance of the population, and that's something that we could demonstrate. But I'll give you a quick, kind of logical statement about it. If we're looking at x bar is going to change. It's going to have its own variance, right? And it's going to range, I don't know, mostly around that 100, right? But we're going to go, 60 below sometimes or 60 above. And every time we run this, we're going to have a different a different sample mean. We're going to have a different x bar. And so this standard deviation or this variance, or if we square rooted it, standard deviation, but this variance is going to be applicable to the sample. And it would be a different story if we knew the theoretic mean, right? It would be a different story if we knew this theoretic mean, because then we could just plug that in. We could plug that in here, and then we would see that Bessel's correction would be helping us estimate the variance of the population, even though we'd be using the variance of the sample. So that's way more than you ever wanted to know about Bessel's correction, and you don't need to know that for the technical interview. This is all to say that we're exploring a concept, and we're using dictionaries, and we're using lists, and we're using some sort of analytic process. So, all that said, let's just move forward. As I said before, standard deviation is just the square root of the variance, and you include Bessel's correction either way. There's kind of a lot of interesting stuff out there on Bessel's correction. So, we have this link to the Wikipedia article, and we have proofs of correctness here that are fun to look at. So, if you want to know more about it, go ahead and read up on it there. Okay. Common plots. Is this what we want to do right now? I might skip this and move on to the next unit. I think this is really important stuff to know. Where are bar plots useful? Where are, what are these variations of bar plots? How do you interpret them? Things like that. But I think more people are working toward the technical interview. So unless there's a specific thing that you want to know from this unit, I'm going to go ahead and skip it and go on to the next unit, sets and set operations. Let's see. So, in general, set theory is a nice way to approach understanding probability, and that's really why we're including it here. Also, Python has this built-in data type called a set, and that data type follows, these kind of behaviors of set theory, and the set operations are, tied in directly to the data type. Sorry, I'm going to go ahead and paste this 126 lines of code, apparently, into the Slack if anybody wants it. I'm not going to put it anywhere else, and I'm about to delete it. So if you want it, it's there. Okay. So, we have kind of a lot on sets here, but I'm going to just I'm going to breeze through a lot of it because, I want to get more into things that are directly important to the technical interview, namely basic probability, a little bit of conditional probability, and discrete probability. So I'll touch on things a bit, but I'm not going to go very deep. So, when we're talking about sets, there are these, important words to consider, to understand. If somebody says an event, what we're really talking about is an outcome or a collection of outcomes of a random experiment. Well, what's a random experiment? It's the result of a phenomena, right? Of a phenomenon. So, it could be a coin flip, and a random experiment is a single flip of a coin. Kind of makes sense, right? Random flip is a random experiment is a single flip of a coin. The event is an outcome from that random experiment, so heads or tails. And we have a couple more words in here, right? Certain or impossible. If an outcome is guaranteed, right? If you have a two-headed coin, then it's certain, and it would be impossible to get a tails. Oh, yeah, that's exactly what it says there. So when we talk about a set, one way that we can define a set is that it is a collection of well-defined and distinct objects. Okay. By distinct, we could as easily have said unique. And the set itself is also an object. And then what becomes really important in our considerations is this idea of a sample space. And this is all the potential outcomes of a phenomenon or of a random experiment, right? So how might we talk about a sample space? And I think this is, an important way to think about this. Let's say you have a fair coin. So you have a fair coin. And you are going to flip that fair coin 3 times. What is the sample space of the outcomes of those flips? So I'll just write a little Python snippet to do this. I'll say, the outcomes, right? The outcomes of a single flip are heads or tails, heads or tails. And I'm going to say for I in outcomes, for J in outcomes, for K in outcomes. And the reason I'm doing this this way is to really try to illustrate that this is like counting. And effectively, we're counting in binary, except we're using H and T. And I'll just print, I'll just print this as an F string, just to have people constantly looking at F strings. So I, J, that should be a J, and K. Okay. So let's see what that does. Here are our potential outcomes. HHH, HHT, HTH, HTT. And if you're familiar with binary, this is going to be familiar. These are all the possibilities. And so we might ask the question, well, you know, what is the probability that we get 3 heads in a row? Well, turns out that's really easy to answer if we know the size of the sample space and we know all the outcomes, right? All the potential outcomes. So 3 heads in a row, that only occurs once in here, and it has to only occur once because this is a sort of counting mechanism. So 3 heads in a row, this is one outcome out of 1, 2, 3, 4, 5, 6, 7, 8. So the probability of getting 3 heads in a row is 1 out of 8. We could ask the question, what is the probability of getting 2 heads out of the 3 tosses? So here's, at least 2 heads. So here's at least 2 heads. This has at least 2 heads. This has at least 2 heads, right? This has at least 2 heads. So 1, 2, 3, 4 out of 1, 2, 3, 4, 5, 6, 7, 8. So 1/2. And we might ask the question, what is the probability? I'll just grab this again because it's all marked up. What is the probability of having the middle values be heads, right? And, you know, we can see that here, 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 here. Again, that's 4 out of 8. And that might lead you to some thoughts about, you know, the types of questions, maybe the nature of a 50-50 split between heads and tails as dictating that probability in some way. So if in this idea of sets, if we know all the outcomes and we know the frequency of those outcomes, then we can discover the probability of a specific outcome or a specific subset of outcomes. And it's pretty straightforward, right? That there's something kind of reasonable about that. So let's see how set union is talked about here. Oh, cool. Oh. Okay, yeah. So I'm going to just talk a little bit about set union and a few of the set operations. I'm not going to do De Morgan's law necessarily. I'm just going to talk about unions and intersections and complements. So let's say we have a set of animals. No, let's do a let's do animals. Okay, so here we've got some animals, and to make a set, you actually instantiate it using the set constructor. That's a dictionary, as it turns out. I actually never use this anymore to instantiate a dictionary because even though it's really common, I think it's confusing. I see this and I automatically think it's a set, but it's actually a dictionary. So I do this. And if you want to create a set with things in it already, you know, you can do that. So dog, cat, rat, mouse, mink. Okay, let's do that. Now, what happens if I try to add another dog in here? Let's print animals. Notice there's only one dog. And that's because sets, mathematically, a mathematical set does not have repeated items. It only has unique items, distinct items, right? And that's going to be true for Python sets as well. So that gives us some options with sets, as I talked about when we were going over Python with this. You can use sets to deduplicate lists. We're not going to do that right now. I just want to show you. So we've got animals, and let's think of that as animals 1 and animals 2. Let's say this is, I don't know, anglerfish and dolphin and rat and mink and squid. Okay, so the union of animals and animals 2 is just going to be all the unique items across both of these. So animals.union, and notice we have this union function. So animals.union of animals 2, this should be kind of a superset that includes both animals and animals 2. So that just gives us all of those results. So that's a union. And intersection, so notice this works both ways. We don't, it's not just animals.union of animals 2. This is the same as animals2.union of animals. And that same thing is going to be true of the intersection. Now, intersection is a little bit different. It's only going to give us the items in common. And, we see this all the time. We see this represented all the time in Venn diagrams, right? We've got these two, we've got A and B. And the intersection is just the things that are shared between A and B, right? So animals.intersection of animals 2. This is going to give us something. If you look at this, if you look at animals 2 and animals, you might be able to guess what that is, right? So let's find out. It's just rat and mink, because that's what's shared between them. So that's intersection. The only other thing I want to touch on here is the complement. Because this is going to come up kind of a lot in probability. The way that I'm going to talk about this, though, is in divergence from sets, okay? So let's try this. Let's create 4-bit binary, all right? I'm going to do for I in range 2, and I'm going to say, I'm going to call this 4-bit binary, and it's going to be an empty list. And then I'm going to append to this list 4-bit binary dot append. I'm going to append I, J, K, L. I actually need to name these I, J, K, and L. And I can say for binary in 4-bit binary, let's just print the binary. And if you're not familiar with binary, that's okay. Let's just kind of peek at it and try to understand a little bit better what's going on here. So we're just counting in binary here, okay? 0, 0, 0, 0, 0 becomes 1, and then it rolls over to 0 and increments the bit to the left. And then it becomes 1, 1, right? Goes back to 1. And there's a pretty nice little pattern here. And notice we're counting from 0, 0, 0, 0 to 1, 1, 1, 1. That's all that's happening there. So we might ask a question. Oops. We might ask a question. What is the probability of getting all zeros? Well, the only time all zeros occurs is right here. So it's going to be 1 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 16. So it's going to be 1 out of 16. Now, what if we ask the question? It just occurred to me I can just actually erase that. What if we ask the question, what is the probability of getting 3 ones, right? Okay, well, we can look through here, and here's 3 ones, and here's 3 ones, and here's 3 ones, and here's 3 ones. So that's 4 out of 16, or 1/4, right? So what if we invert that question? What if we ask, what is the probability of not getting 3 ones? Well, that's just going to be 1 minus 1/4, right? Because it's going to be everything else. So that's a simple way to think about the complement. And the complement really isn't more complex than that. But it comes up so much in probability where we're trying to figure out, some value, and it's easier to calculate the complement of that value and then subtract it from 1. So just understanding, that there are going to be times where leveraging the complement is more convenient is important. Okay. So I think that's all I want to cover out of sets and set operations. And the way study hall, generally goes is, in most cases I'm actually swamped with questions, and I'm not actually working through a lot of these materials, but I go end to end on these things over time. But since we're coming down to the wire with interviews, I'm skipping over a lot of intro to stats and just touching on certain things that I think are relevant to the technical interview, immediately relevant to the technical interview. So basic probability. Yeah, let's look at notation for a second. So first off, let's look at this idea of cardinality. Cardinality is simply how many possibilities there are, how many possible outcomes there are. And this is often the divisor in our probability calculation. So, the cardinality of the larger set, right? And that is our denominator, whereas the cardinality of the subset of S is the numerator. And that's kind of what we just saw with that binary, where, we're asking, the cardinality of the subset of 3 bits divided by the cardinality of the entire set, which was 16. So we ended up with 4 over 16, or 1/4. So in terms of notation, you're going to mostly see P of A. A lot of people write probability of A in much better handwriting than this. That's not as common. P of A is fine. A with this superscript C, this is the complement of A. This is an AND operation, right? This is an intersection. The probability of A and B, or the probability of A intersect B, probability of A union B. Sometimes you see this as also as A, kind of this upside down U B, right? Those mean the same thing. I usually actually write this out just because I do. And this is A given B. So these are just the common ways that we're going to have these written, the notation that we're going to have throughout these materials. I'm going to focus, I think, just on an idea of mutual exclusivity. And I'm going to take kind of a high-level view of this. So let's say we have let's say you have a 5-sided die and a 6-sided die and a fair coin. Okay. So let's ask the question, what is the probability that you get a roll of 4 with the 5-sided die, then a roll of 4 with the 6-sided die, and then a heads? So the thing is, whatever you get when you roll the 5-sided die, whatever that is not going to affect the roll of the 6-sided die or the flip of the coin. And so those events are mutually exclusive. They do not affect each other. And as a result, we can simply calculate this. We can say, well, it's a 1 out of 5 chance multiplied by a 1 out of 6 chance multiplied by 1 out of 2. So this is our actual probability here. And that's pretty low. It's not super low, but it's pretty low. So 1.6 chance that that's the outcome. Now, we could go quite a bit deeper into this. I think for now I'm going to skip permutations and combinations. I've gone over those a number of times in study hall, but I do want to, revisit. For the moment, I want to revisit factorial. So we expect you to be able to write factorial on the spot without looking at anything. It's just something you should know how to do. So factorial of n, some number, I'll just say num. I'm going to have some product that gets returned. Now I can't initialize this at 0 because 0 times anything is going to be 0, so I'll initialize it at 1. And I'll say for n in range to from 2, I'll start at 1, doesn't really matter. 1 to num plus 1, because I want to include that number. The product is going to be increased by multiplying by n. And then I can just return the product. So if I run this on 5, I should expect 120. Oops, 5. And I get 120. So a way to think about this is sort of in terms of the arrangements of a number of items. Okay, so I might ask the question, you have a deck of playing cards, of standard playing cards, right? How many different ways can this deck of cards be shuffled? And offhand, this is just a massive number. So it's factorial of 52. And notice this number is so massive that the computer, my computer, doesn't have enough precision to tell us what these values on the far right are, right? This number is just too big. And so it's like, you know what, we're good. We're close enough. You know, we don't actually care about this. What is this? Over a trillion, right? We don't care about that. It's not consequential given the size of this number. Now, we can use this to inform ideas of permutations and combinations, and I'll come back to that another time. But I just want to show you there's this idea of, you know, cardinality, right? These are all the possibilities, and that's what we're seeing when we run factorial. We're looking at all the possibilities of arrangements. And that's arrangements where we don't repeat or we don't replace, right? If we have a single, you know, we're not going to have 52 Queen of Diamonds, for instance, in this problem. Queen of Diamonds is only going to appear once. Okay. So let's mess around with let's mess around with Poisson for a little bit. So the interview that you get, the technical interview you get, might cover Poisson. And, well, oh, I still need that factorial function. So if you're covering, if you need to write Poisson, well, you're going to need factorial. Factorial is in Poisson. And we would provide you with the Poisson formula for the PMF, okay? What this is going to tell you, the Poisson PMF tells you the probability of a certain number of events occurring given that you know the average number of events that you would expect to occur, okay? So there are multiple components here. We've got lambda right here. This is lambda. That's our expectation. That's our average number of events that we would expect to see. We have Euler's number here, 2.71828. It's something like you can think of it sometimes as a decay factor that's super common in the universe. And then we have K, which is our the number of events on which we're trying to find the probability, right? So what's a sort of kind of classic Poisson problem? You are, let's say you're reading a book. You see the word "the" appear 20 times every 5 minutes on average when reading. What is the probability that you will see "the" appear 30 times in the next 7 minutes? Now, any time you're dealing with Poisson, you want to think about constraints. Let's say that stylistically, nothing is changing in this book. You know, earlier chapters have the same writing style as later chapters. Distribution of words is fairly constant. And you can answer this question, but it has to be held within these constraints. So you see the word "the" appear 20 times every 5 minutes, right? The word "the" appear 20 times every 5 minutes. So we have a lambda initially. We have this initial lambda that is 20 for 5 minutes. But we need to modify this lambda in light of the question, because we want to know the probability of seeing 30 in 7 minutes. So we actually need to think, well, 7 minutes divided by 5 minutes, that's going to be the growth factor of lambda. And then we can, we know our value of k, which is 30. That's the number of events on which we're searching for the probability. So with all of this, let's just go ahead and write the Poisson PMF. Let's say def Poisson PMF, and we need lambda and we need k. We're also going to need e. So I'm going to say from math import e. That's easy. And I'm going to say, I'm just going to return lambda raised to the k multiplied by e to the negative lambda, and all of that divided by the factorial of k, right? We defined factorial up here, so we can do that. So I've got the Poisson PMF. I can answer this question now. I can say, well, our lambda is lambda, which we defined above, and our k is k, which we defined above. And I'll just print this out. And we can find out the probability that we're going to see the word the appear 30 times in the next 7 minutes. So that looks like 0.0677, right? What if we ask the question, what is the probability that you will see the word the appear more than 30 times in the next 7 minutes? So this presents a bit of a problem because more than 30 times is 30 to infinity. So you might think, well, that's an issue. But it's not that much of an issue if you consider that probabilities can't be greater than 1. And we know that we can calculate the probability of the appearing 0 times, 1 time, 2 times, 3 times, all the way up to 30 times. And if we sum that, that is going to be the complement of the probability of the word the appearing more than 30 times, 30 up until infinity. So 1 minus the probability of less than or equal to 30 is essentially what we want to do here. So I'm going to take this, I'll just put this up here, comment it out, and I'm going to essentially make a cumulative function, okay? So I'm not going to write a clear function on this, I'm just going to do this in a simple way. I'm going to say less than equal. Sometimes you see less than equal written as LTE. So if you see LTE and you're like, I don't know what that is, it might be less than equal, and that might explain what's going on. So less than equal to, I'll just say less than equal to 30. And I'm going to start that at 0, and I'm going to make this an accumulator pattern. I'm going to say for k in range, we'll go from 0 to 30. I usually do 30 plus 1 because 30 is sort of an important number, but I want to include it, so I just say 30 plus 1. That's a convention I use. And then I'll say LTE sub 30 is going to get incremented by the Poisson PMF of k with our lambda, which I think we're just going to use the same lambda. Yep. So I'll just do that. Oh. Should probably actually copy the whole lambda. There it is. Okay. So whatever that is, 20 times 7 over 5, it's fine. And now, so first let's print less than or equal to 30 and take a look at that. We would expect this to be under 1, maybe well under 1. So 0.69, essentially 0.69. And if I want to answer this, I can just do the complement, which is 1 minus 0.69, etc. Oh, should probably save that. 0.3096. So that's the probability that we're going to see the word the appear more than 30 times. Okay. So I'm going to call it here today. And we're going to have study hall again tomorrow. Same time, 4 p.m. Mountain Time, 3 p.m. Pacific, 6 p.m. Eastern. And I'll probably spend time with these distributions, mostly binomial. I'll continue with Poisson a bit, and then look at binomial and then geometric. And we'll bring some dictionaries into this, some analysis. We'll just think about different kinds of problems and play around with them. Yeah. So thanks for watching, and as always, bring your questions, bring anything like that whenever you're stuck. Oh, somebody just asked a question. What question would 1 minus the probability mass function of 30 answer? Oh, that's a great question. Let me answer that. And I will share my code. So I'll finish this and I'll share this code. So what question would 1 minus the probability mass function, right, the Poisson PMF, I'll just grab that, 1 minus the PMF of 30 answer? So the Poisson PMF of 30 is the probability that exactly 30 occurrences of the word the would appear in 7 minutes. And let's assume this is our same lambda as before. So I'll put that in there as well. And the answer here is just the question that would be answered is, what question would 1 minus? It would answer the question, what is the probability that the word the does not occur 30 times in the next 7 minutes? So it could occur 0 times, or 1 time, or 29 times, or 5,733 times. That's like any other possibility than 30. So this would be sort of a pure complement right here. This is actually the complement of the CDF of lambda, comma, k less than or equal to 30 up here. But this would be the complement of the occurrence of 30 times, of the word the 30 times. Okay, so I'm going to go ahead, paste my code in. And I will try to pick up from here tomorrow. Yeah, I think we'll use some dictionaries. I think we'll maybe do some transformation of these problems, and we'll kind of explore things in a way that looks like the technical interview. Okay, so thanks so much, and bring your questions tomorrow, and anything where you're stuck on Learn, definitely bring it tomorrow, and we'll continue kind of in this vein of kind of picking and choosing things that are in the Learn materials. And after we get out of this, big interview rush, I will dig deeper into the other materials in the stats space.